Welcome to experiment 2, and for experiment 2 we're going to be studying what's known as a frequency filter. Okay, so for this circuit what we're going to need is our 10 kilo ohm resistors, okay, and our 10 nanofarad capacitors. So as with the case whenever we're working with new resistors, we want to measure what their exact value is. Okay, so if you remember from experiment 1, how we get our resistance, you just pick two random points on your circuit board to plug in your resistor. Then we've got our multimeter again. So we know this resistor should be about 10 kilo ohms. So if we set it to the 20K range, it should be fine. One probe on the one side, other probe on the other side. And we see that this resistance is 9.97 kilo ohms, which we'll take note of. Okay, so now to build our circuit, what our input's going to be is an AC signal. So we know that to get our AC, we come to this point here below the out. We connect one part of our wire to there, the other part to a point in our board. Okay, and then we need the voltage from that pink wire to flow into one side of our resistor. So our resistor, one leg goes into the same voltage line as the pink wire, and then the second leg goes into its own voltage range there for current flow. And then the new component we're introducing is the capacitor. Okay, so we've got our capacitor, and just like before with our resistor, we want one leg going into the output of our resistor, and then the other leg going to its own voltage range here. And then finally, to complete the circuit, we just want to take the output of our capacitor and send it to ground. Okay, so once we've got our circuit set up, we need to adjust our input source, our AC source, to the correct range we want. Okay, so how we're going to do that is you take your oscilloscope probe, we're going to plug it into our input. Okay, so you'll see now we've got our voltage reading on the screen, but we're going to need our frequency reading as well. So we can push the measure button, still source of channel 1, but now we go to our time range, and we're going to scroll down to frequency, push enter, and now we'll see it's giving us our frequency of our signal as well. Okay. So we'll see for this experiment, what we want to do is set our frequency to 500 hertz. So how we're going to do that is we first set the correct range of our frequency. So we'll see when I set it here, it means our frequency will vary between 100 hertz and 1 kilohertz. And then to get to the specific 5, we use this fine-tuned dial in the top right-hand corner. So right now at that edge, it would be at the bottom of our range, 100 hertz. So to get to our 500, we just scroll it up to roughly the 5. And you'll see now, when you get stars for a value here, it means that your scale on your frequency range is too low for it to get the full picture. So all we do is adjust our scale until we get a complete wave in. And now we can see we've got the full picture and our frequency, and we can just fine tune it to get closer to our target of 500 hertz. Okay, so we've got our correct frequency. Our correct voltage is just turning up the amplitude to maximum. And then finally, we want our correct signal type, which is the sine wave we see on the screen here. So now with this circuit, we need to be able to monitor both the input and the output at the same time. So that's when we introduce a second probe where we plug in to our channel 2. Okay, and then we just turn on our channel 2. Set it to similar settings as channel 1 to begin with. Okay. Okay. So now what we can see is if I plug in channel 1 is our input, as we had before, and plug in channel 2 for our output, we see we can get 2 different signals. Okay, so what you should see on the screen, now currently the input and output are in the same range, so what that means is why we've got an overlap there, but you'll see if I change the scale of one of them, so now the yellow one is our input and the blue one is our output. So we can monitor how those two change. Okay, so we're going to now switch into the next wave type we need, which is the square wave. Okay. So what we're going to see for this one now is that our yellow, which is the input wave, gives us this nice square shape here. But what you'll see for the output, it's got this curve down and up feature here. So you'll see it curves down to 0 instead of going straight down, and then it curves up again instead of going straight up like the input. So that's the behavior we're interested in for this experiment, or part of the experiment. Okay, so now what we want to do is measure the time it takes for the output to decrease from its maximum to the 0 point along our graphic here. So this line down the center here is our 0 point, and we want to determine the time it takes for our output to drop from there, the maximum, down to the 0 point. So now that's going to introduce a new feature called the cursor function. Okay, so for this one, we can freeze it so long so we don't have to worry about variation, and you can turn off channel 1, our input, temporarily, okay, and then just expand our output to a larger size that's easier to work with. Okay, so now this cursor function I'm talking about is, you'll see below the measure button we had before, we've got this button that says cursor. So you're going to keep pushing it until your mode goes to manual, and we want our X type here. And you'll see when I did that, it introduced these 2 dashed lines here. Now those are our cursors that we're going to use to measure that time drop. So you'll see right now that it's highlighting cursor A. Okay, so then when I move this thing here, you'll see cursor A is the one that's moving, the white line. So what I want to do is you move it to the point where it's just about to start dropping from the maximum. Okay, and then we want to move cursor 2. So what you do is you push this button. So we see now we're on cursor 2 or cursor B. And now when I adjust this, it moves our yellow dashed line. So you're going to move it to where our blue output just reaches that 0 line here. Okay, so now we've got our cursor A, or first cursor, just at the maximum where it's about to start to drop, and our cursor 2 or B, just where our output crosses the 0 line. And now you'll see there, this delta X value is what you want to take note of in your results sheet. So now the alteration to the circuit that we want to make to get different time drops that we just measure with the cursor function is by increasing our resistance in incremental amounts. So we started off with 10 kilo ohms. What we want to do is increase it to 20. So we just take a second 10 kilo ohm resistor. As per usual, you always want to make sure you know what the exact value is. So we come back to our multimeter, set it onto our resistance range, measure the value. Okay, then you take note of a resistance being 10.04 kilo ohms. Okay, and then we add our resistor in series to the first one. Okay, so we've got our new circuit here. We've now got 20 kilo ohm resistor to the capacitor. We're going to take probe 1 as our input again. And then probe 2 will be our output. So it's going to be after the second resistor because we want our full resistance of 20. So it'll be where the capacitor and the resistor meet. Okay, so now what you'll notice from our screen is that the drop is now more drastic than it was before. Okay, so you'll see then it's going to be a different time difference between the drop from maximum to 0. So once again, we can freeze our picture. We can turn off channel 1, make our output a little bit bigger for convenience, and then we use our cursor function again. So push cursor to get it to manual mode, X type, and then we just adjust our cursors again. So you'll see then that our input cursor, A, is conveniently on the maximum point again. So we just need to change cursor B to our new 0 point. Okay. So now you'll see that the delta X, the difference between the two cursors, has increased. Okay. And then that's all we're going to do for this part is we'll increase our resistances in increments of 10 kilo ohms up to 50 kilo ohms and measure the time drop for each of those resistance combinations. And you should notice that as the resistance goes up, so does the time difference. Okay, so now we're going to move on to part 2 of experiment 2, which is known as the low pass filter. So the circuit structure is basically what we had for right at the beginning of part 1. You've just got your 10 kilo ohm resistor getting its alternating current input, and then the resistor goes out to our 10 nanofarad capacitor, which then the output goes to ground. Okay, so what we want to do for this one is we start off with the same initial settings as we had before, maximum amplitude, frequency at about 500 hertz, but now we're switching back to the sine wave instead of the square wave. Okay, so what we'll do then is use our 2 probes again. We're going to use probe 1 as our input, and probe 2 is our output. Okay, just adjust to get a fuller picture. Okay, now we're going to study the effect on this circuit by altering the input frequency. Okay, so first thing we want to do then is you'll see that as we increase our frequency, our output starts to drop. So you'll see the blue curve here is that as I'm increasing the frequency, our blue curve is starting to decrease. Okay, so what we're looking for is we want to first find the point where our output is at what's known as a special point of the 3 decibel point for the circuit. Okay, so how we identify that is we look for the voltage of our output to be equal to our input voltage divided by square root 2. Now, from the theory, you'll understand where that comes from. Okay, so on our screen, we currently have our voltage for our input and the frequency for our input, but we also want to see what the voltage for our output is. So we go to measure, we're on channel 2, so we can select voltage Vmax again, remove the menu, and now we'll see here that we've got our output voltage too. Okay, so if we look at our input, Okay, we've got that our input is about 5.52 volts. So if we divide that by square root 2, that should roughly equal about 4 volts. Okay. So now what we want to do is we keep increasing our frequency of our input until we get to about 4 volts. Okay. Now this is the point we're looking for, known as the 3 decibel point of our circuit. And you're going to take note of what your input voltage is, what your output voltage is, and what your exact frequency is. So now that we've got our 3 decibel frequency, what we want to do is find the phase shift between our input and output. Okay, so you'll see now that as we were changing our frequency, we no longer had the peaks of our input and output perfectly aligned. They start shifting apart as the frequency changes. So the phase shift then is going to be the time difference between the peak of the input, the yellow, and the peak of the output, the blue. Okay, so now we're going to be using our cursor function again. You'll push your cursor button, keep going till manual. We're still stuck with source X. Okay. Then we're going to now adjust our cursor until we've got cursor A is going to be at the peak of one of our signals, in this case the input, and then cursor 2 is going to be at the peak of our output. Okay. Okay, so now we'll see we've got cursor there, and now the delta X will give us the time difference between our input and output. Now what you need to take note of that the oscilloscope doesn't give you is you need to assign the direct or sign yourself. So what I mean by that is you'll see now in this picture here, we've got that our input is peaking first. So when the input peaks first, we want to record our delta X as a negative value. So you would then take this down as negative 72 microseconds instead of just 72 microseconds. So now the alteration we want to make to the circuit to study how the output changes is just by varying the frequency. So now that we know what our 3 decibel frequency is, which is this roughly 1.9 kilohertz, we're going to change our frequency to different multiples of that. So you would work out on your calculator what an estimated 1/12 of the frequency is. So if we did that, that would be roughly, say, 800 hertz. So you're going to then adjust your frequency down to 800 hertz. Okay, put a clearer picture. And then we're just going to repeat the same procedure. You'll record your input voltage, your output voltage, and your exact frequency. Okay, and then we're going to use our cursor function again to find out what the time difference between our 2 peaks are. Okay, so we do cursor, manual, X type again, and then with these ones you're always free to adjust the picture to a better size so you can see. So now we're going to move our cursor A, the white one, so it's at the peak of our input again, and then we'll move our cursor B, so it's at the peak of our output again, and then we'll record there. So we'll see with this one that our input peak is still coming first. So when you record this delta X, you're going to record it as negative 80 microseconds instead of just positive 80 as it shows you on the screen. Okay, then we'll change our frequencies into as multiples of our 3 decibel one. So we started at 1/12, then you'll go 1/9, 1/6, 1/3. Got our 3 decibel ready, and then we will start going to 3 multiples. So we'll do 3 times, 6 times, 9 times, and 12 times. And I'll just demonstrate now what the 12 times looks like. Okay, so if we turn off our cursor function again, run our system. So 12 times our 3 decibel frequency was roughly 24 kilohertz. So we're going to set our frequency of the input to 24. Okay, so now we'll see that we've got roughly at 24 kilohertz, which is 12 times our 3 decibel. You can freeze again, and then as with before, you record your input voltage, your output voltage, your exact frequency, and then you'll use your cursor function again to determine the time difference between the peaks. Okay, so if we move cursor 1 to the peak, the input, and then cursor 2 to the peak of our output. Okay, and then we'll record our delta X value again. And once again, we'll see in this case here that we've got our input coming first or before our output. So we'll record our delta X as negative 9.20 microseconds. Okay, so the last thing we need to consider doing for this part of the experiment is some of the outputs and inputs you see on your oscilloscope you want to take a picture of. So how you do that is you can just freeze on a particular frequency, okay, and then you just use your cell phone or any other camera device to take a picture of what you see on the oscilloscope screen, making sure to catch what the voltages are and what the frequency is. Okay, so now we want to move on to part 3 of experiment 2, and that's now what's known as a high-pass filter. So the only alteration you need to make in the circuit between what you had for part 2, the low pass, and part 3 is by switching our resistor and capacitor around. Okay, so now we have our AC current flowing into our capacitor, which then flows out to our resistor, which finally flows out to our grounding source. Okay, so for this one, we're going to want to start off with a similar input type. So we can use our first probe to take a look at our input. Okay, so what we need to start off with is maximum amplitude, okay, a sine wave, and now we want our frequency to be at roughly 500 hertz. Okay, and then we can attach our output probe again to see what our input and output looks like. Okay, so once again, we're going to want to measure the time difference between our input and output. So we'll start off with our cursor function again, change it to manual, still time type X. Okay, so we'll move our white cursor to the peak of, in this case, our output, and then we'll move our yellow cursor to the peak of our input. Okay, so now you'll see what's different between the high pass and the low pass is we now have our output coming first. So because the output's coming first, you would just record your delta X value here as the positive 400 microseconds instead of making it negative 400 microseconds. So because we're dealing with the same capacitor and resistor as part 2, the low pass filter, it means that our 3 decibel frequency should occur at roughly the same point. So we're going to adjust our frequency to the 1.2 kilohertz we had from part 2. Okay. So once you locate your 3 decibel frequency, you're going to want to do determine the phase shift again between your input and your output signal. So we bring on our cursor again, manual type X, adjust our white cursor or cursor A, so it's at the peak of our output. And then we move our yellow one to a peak of our input, the yellow curve. Okay, and then once again we can see because our output is coming first, we can just record our delta X as 96.0 microseconds instead of negative 96. Okay, so now, just like with part 2, the change we want to make to our input is just varying our frequency and seeing what effect that has on our output. So we know what our 3 decibel frequency was, roughly 1.2. So we're going to go to 1/12 of that again, which is around about 800 hertz. Okay, and then we just do the same as usual, record our voltage of our input, our exact frequency, and our voltage of our output. Okay, and then we want to measure again what the time difference is between our input and output. So we turn on our cursor. Okay, going to move cursor A to the peak of our output, cursor B to the peak of our input. Then once again, because our output's coming first, we can just record our delta X as positive 220 microseconds. Okay, then while you're changing your frequencies to different values, it is recommended that you take a few pictures of what you get on your oscilloscope screen. So you just use your phone camera to take a picture of what you see on the screen, making sure you get in your frequencies and voltages. And then you just, once you've done that, you can adjust to your next frequency. Record your values again. Use your cursor to find your time difference. Okay, you record your time difference again. Remove your cursor, take a picture, and you're just going to do that ranging frequencies from 1/12 of your 3 decibel point up to 12 times your 3 decibel point in steps of 3. So 12, 9, 6, 3, and so on.